Alright, so in this lesson here, you're going to be looking at how we can use finite differences to determine the degree of a particular polynomial. So looking at this example here, we're going to be looking at a set of data and be able to determine, using finite differences, what the degree was. We're only going to be looking at 5 different kinds. In this case, we're going to be looking at linear, quadratic, cubic, quartic, and quintic. And based on the number of differences it takes to get the differences to be the same, that'll determine what kind of polynomial we're looking at. So let's just take a look at the example. So one thing that you do need to note first is notice the x's along the top. One thing I notice about those x's is that there is a definite pattern there. Can you see it? Notice that those x's are changing by a constant amount. They're each going up by 1. That will allow us to now focus our attention to the y's. So let's take a real good look at those y's now, and let's go ahead and find the differences as we increase x. One thing to note here about these values is as you go from -10 to -4, we're going to find the difference change there, and from -4 to -1.4, we're going to find the change there, and we're going to continue this pattern until we get to the very end, and we're going to be finding differences along the way. So let's go ahead and find those changes. Note that the first differences, going from -10 to -4, we increased by a value of 6. Going from -4 to -1.4, we increased by 2.6. -1.4 to 0, we increased by 1.4. We increased by 2.4 to go from 0 to 2.4. And finally, we increased by 5.6. A couple ways you can do this. You ask yourself a question. If I'm going to go from -10 to -4, how far did I go? Well, we had to go up. And how far up did we need to go? We need to go up by 6. One other way you can find is take the -4 and subtract the -10. And that can help you arrive at 6. And we come to an important conclusion here when we look at those differences. One thing that we notice about those differences is not the same change. And so when we look at these changes here and we notice that it's not a constant rate of change, what that tells us now we have to look at the second differences. So where we're going to get the second differences from is by doing differences of those red numbers right there. Let's find the change going from 6 to 2.6 to 1.4 to 2.4 to 5.6. Let's find those. And so when we find those changes, notice that we actually were going down here, going from 6 to 2.6, we actually decreased by -3.4. So to represent that, we're going to go ahead and use a negative value. We do the same thing going from 2.6 to 1.4, we also decrease by 1.2. Going from 1.4 to 2.4, we increase by 1, and then we increase by 3.2. We still don't have a constant change. So now let's look at our third differences. Maybe we might pick up something there. Aha, now we got someplace. Notice the third difference is there. Third difference is we increase by 2.2 and increase by 2.2 and increase by 2.2. We now have a constant change, and that constant change is 2.2. So what do we do with this information? Well, now we take it over to our polynomials, and then we determine that because it was the third differences that was giving us a constant change, we have now determined that the best polynomial for this function would have to be a cubic polynomial. And that's what those differences allow us to do, is allow us to figure out after a certain amount of differences, once we get those differences to be the same, now we can determine that it was indeed cubic. Now, the other thing that you need to be looking at here in this section is also being able to determine a couple things here. In the math biz, we can separate polynomial functions into 2 different kinds of groups. One group is odd degree functions, another group is even degree functions. So when we look at odd degree functions and only odd degree functions, something significant jumps out. So let's just take a real good look at those odd degree functions. One thing I notice about those odd degree functions is the arrows. If we take an even closer look at those arrows, we can make some important conclusions about possibly all odd degree functions. One thing I notice about the first degree function is that one arrow goes up, the other goes down. We notice that with the third degree function. One arrow goes up, one goes down. And with the fifth degree function, one arrow goes up and the other arrow goes down. So this is a very, very powerful assumption that we can make with these odd degree functions, is that all odd degree functions, those arrows, one goes up and one goes down. Now, is the right arrow always going to go up and the left arrow always going to go down? I don't think so. Sometimes we can flip it around. Sometimes the left arrow will go up and the other one will go down. But one thing that we can conclude here is that those arrows all go in opposite directions. Now, what if we look at the even degree functions? It's pretty clear to see that the arrows don't go in opposite directions. We can see here for the quadratics, arrows go in the same direction. Notice in this case they both go up. Same is true for fourth degree functions. So with all even degree functions, the arrows are going to go in the same direction. They can either go up all the time on both sides, or they may go down. Okay. Now, when you look at these polynomials here, we can also determine whether the leading coefficient was positive or negative. If we take a look at the top row of polynomials, the odd degree function in the upper left and the even degree function in the upper right, let's take another close look at these. And I'd like you to notice the right arrows. Do you notice on the odd degree function, the right arrow goes up? And you also notice that the right arrow goes up on the even degree function as well. And when that right arrow goes up, what we can conclude about this polynomial is that the leading coefficient must be greater than 0. Now, we don't know what the equation even looks like here, but one thing that we can conclude about this thing is that the leading coefficient had to be greater than 0, aka that leading coefficient had to be positive. So let's take another step back now, and let's shift our focus now to the bottom row. Let's look at the 2 down below. And when we look at those 2 down below, let's look at that same right arrow again. Notice that right arrow this time now goes down as it goes to the right. And once that right arrow goes down as it goes to the right, what we know now about that leading coefficient is that leading coefficient must be negative, or in other words, less than 0. But for your purposes here, we're just going to simply say that leading coefficient is negative. So let's take a look at these 2 examples here. Let's take a look at the one on the left, and let's try and determine if it was an even or odd degree, and also we can determine if the leading coefficient was positive or negative. So taking a real good look at this one, at part A, one thing jumps out at us. We know that the arrows point in opposite directions. So that means that the polynomial must have been odd. We can also take a look at the right arrow, and what we notice about the right arrow is that it points up as it goes to the right. So if that right arrow goes up as it goes to the right, one thing that we can now conclude here is that the leading coefficient must have been positive. So our final conclusion we can make here about this polynomial function, we might not know what the exact equation is, but what we do know is that it was an odd degree function, and we also know that the leading coefficient had to be positive. Now that we shift our focus over to the B over there, what we notice is that both arrows point down. Because both the arrows point in the same direction, now we can clearly see that the degree needs to be even. Also notice that the right arrow, as you can see right there, goes down as it goes to the right. So what that tells us is that the leading coefficient must be negative. Okay, so that's pretty much everything that we need to know here to handle this work. Happy math!